Zeros of a polynomial function. Let's do the long division of f of x, which is 5x cubed minus 8x squared minus 19x minus 6 divided by x minus 2. So here we've set up the long division, and the first thing we want to do is we want to divide 5x cubed by x. 5x to the third divided by x is 5x to the second. So I put that first term of the quotient up here, and then I'm going to multiply that term by the binomial x minus 2. So 5x squared times x will give me 5x to the third power, and 5x squared times negative 2 will give me negative 10x squared. Next, I'm going to subtract this binomial from the dividend. So I'm subtracting here, and since I'm subtracting, I have to distribute that negative. If I distribute the negative, this becomes negative 5x cubed, and this becomes positive 10x squared. And then I'm going to just combine the like terms. These will cancel out, and then negative 8x squared plus 10x squared makes 2x squared, and I bring down the negative 19x, and I bring down the negative 6. 2x squared divided by x is 2x. So I put the second term in the quotient up here, and I'm going to multiply that 2x by x minus 2. So 2x times x will give me 2x squared, and 2x times negative 2 will give me negative 4x. So I subtract this from 2x squared minus 19x minus 6, which means I have to distribute this negative. This becomes negative 2x squared and positive 4x. And then I'm just going to combine the like terms. Negative 19x plus 4x makes negative 15x, and I bring down the negative 6. And now I'm repeating the process one last time to see how many times x goes into negative 15x. Negative 15x divided by x is negative 15, and I'm going to multiply that negative 15 by x to get negative 15x. Multiply that negative 15 by negative 2 to get positive 30. So I'm subtracting this, and that means I have to distribute this negative, changing this to a positive 15 and a negative 30. And then I combine the like terms. These will cancel, and I get here negative 36. This trinomial that consisted of the terms I got when I did each of these individual monomial divisions is called the quotient. That's what they're asking me to find. They say find the quotient. But there's another number down here, this negative 36, that represents the remainder. There's another method called synthetic division that we can use to find this quotient and remainder. To do synthetic division, first, you set up your division this way. You take the opposite of this number, you change the sign so that you can account for all the times you subtracted here. So by changing this sign, you don't have to worry about that subtraction. So I put a positive 2 here instead of a negative 2. And then I'm putting the coefficients of the dividend. 5, negative 8, negative 19, and negative 6. And I put a bottom line down here. Now I'm going to start the synthetic division. First, I bring down the 5. And you notice that 5 was the first coefficient in the quotient. Then I'm going to take the 2 and multiply it by the 5, and I'm going to get a 10. And I'm going to put that 10 above the horizontal line. That 10 is the same 10 I got here. And notice that 10 I can now add to the negative 8 to get the next thing I'm looking for. If I add this negative 8 and this 10, I'm going to get the 2. 2 is actually the coefficient of the next term in the quotient. Then I'm going to take that 2 and multiply it by the 2 up here. So I'm multiplying the 2's, and I'm going to put the result here, and that's a 4. When you have something above the line, you're going to add it to whatever's above it. This is the same sum I did here of 4 and negative 19. So 4 and negative 19, when I add those, I get the negative 15, which is actually the last term in the quotient here, negative 15. And then I'm going to multiply the 2 by the negative 15 and put the answer up here. That is the negative 30 that was the result here. Negative 30, and then I can combine these, the negative 6 and the negative 30, to get negative 36. So you can see here that I have all of the coefficients of the terms in the quotient here, and I actually have the remainder here. So when you do this synthetic division, you can ignore the variables and you get the coefficients of the quotient and the remainder without having to worry about them. Now, there's something else I want to talk about. It's actually called the division algorithm. And the division algorithm says this: if f of x is a polynomial of degree n greater than or equal to 1, and dx is a monic linear binomial of the form x minus c. So this is monic because the leading coefficient is 1, and it's linear because the degree is 1, and it's a binomial because there are two terms. So if we have a monic linear binomial of the form x minus c for some complex number c, then there is a unique polynomial q of x and a complex number r such that f of x, the original polynomial with degree n greater than or equal to 1, is equal to x minus c, which is that binomial, times the q of x, which is that unique polynomial they're talking about, plus r. The q of x they're talking about here is called the quotient, and r is called the remainder. So basically this says that you can write any polynomial as the product of x minus c, a quotient, and the addition of that to some remainder. If r is equal to 0, we say that x minus c and q of x are factors of f of x. In this case, we have this quotient q of x, we have this remainder r, and we have this original polynomial f. And what they're saying by this division algorithm is I can write this as f of x, which is this original polynomial, equals x minus c, which in this case would be just the x minus 2, times the quotient q of x, which is that same quotient we got. Here are the coefficients of it. And then plus the remainder. So that's plus negative 36 or minus 36. So this is the division algorithm. Let's take a look at it in action one more time. So here we're dividing by x minus 2. Let's divide by another monic binomial. Let's divide instead by x minus 3. So in this case, the value of c is 3. I'm going to put 3 in that little bracket. And I'm going to do this synthetic division for x minus 3. I'm doing the same polynomial f of x. So let's see. First, I'll bring down the 5. And then anytime something is below that horizontal line, you multiply it by the 3. And put the answer above the horizontal line in the next column. So 3 times 5 is 15. And then I add anything above the horizontal line to whatever is above it in that column. So negative 8 plus 15 is going to give me 7. And once again, this is below the line, so I multiply and move it up to the next column. That's 3 times 7 is 21. And then I add now. Negative 19 plus 21 is equal to 2. And then I multiply when it's down here. So 3 times 2 is going to give me 6. And then I add when it's up here. So negative 6 plus 6 is going to give me a remainder of 0. Here's what I have. I have that I can write this now using the division algorithm as x minus c, which is x minus 3, times the quotient, which is 5x squared plus 7x plus 2, and then plus the remainder, which in this case is just plus 0. You know that addition of 0 is trivial. You don't have to write plus 0. So here what I have is that the original polynomial f of x is equal to this product, x minus 3 times 5x squared plus 7x plus 2. So whenever the remainder is 0, then x minus c and the quotient are actually factors of the original polynomial. So that is the division algorithm. There's a theorem we need to look at. It's called the remainder theorem. And the remainder theorem says if the polynomial f of x is divided by x minus c, which is what we've been doing, then the remainder is the f of c. Here you can see that here if we take a look at the division algorithm, which guarantees the q of x, which is that polynomial, that unique polynomial, the remainder r, and x minus c as a factor here. If we were to plug c into this division algorithm, you'll see that we get that the f of c is equal to c minus c times the q of c plus r. But c minus c is equal to 0. And then 0 times the q of c is equal to 0. And 0 plus r is r. So if you divide the polynomial f of x by x minus c, the division algorithm guarantees that you can find a quotient q of x that is unique and a remainder r such that this will be true. If we plug c into this form, the division algorithm, then we get that the f of c is equal to r, the remainder. And that is the remainder theorem. So basically, if we look back at what we did earlier here, we can recall that we said we can write the f of x this way for the original division that we did when we divided f of x by x minus 2. If we plug 2 in for x, because this is x minus 2, we will get that the f of 2 is equal to 2 minus 2, which is 0. And then this is 5 times 4, which is 20. 2 times 2, which is 4, and there we have the minus 15. But then 0 times this sum, where this sum is equal to 9, is still going to be 0. And this is going to give us 0 minus 36. So we get that the f of 2 is equal to negative 36, which, remember, that was the remainder. So indeed, if you divide the polynomial f of x by the monic binomial x minus c, then the remainder, which in this case is negative 36, will be the same as the f of c, which is the f of 2. All right, let's take a look at using that in a different situation here. Let's consider the polynomial f of x equals 3x cubed minus 2x squared minus 9x plus 27, and the completed synthetic division down here. So based on what we just learned, this is the remainder, and these are the coefficients of the quotient. So since this is the remainder, that means that by the remainder theorem, the f of negative 2, which is the f of c in this case, is equal to the remainder, 13. Without having to plug negative 2 in for all the x values here and do that arithmetic, just by looking at this, I know that the f of negative 2 is 13 by the remainder theorem. There's one last theorem we need to look at, and it's called the factor theorem. So the factor theorem says if you let f of x be a polynomial, if f of c is equal to 0, then the monic binomial x minus c is a factor of f of x. And also, if x minus c is a factor of f of x, then the f of c is equal to 0. Let's take a look at that in action. Consider the polynomial f of x equals 7x cubed plus 38x squared plus 13x minus 10, and the completed synthetic division below. So I see the completed synthetic division here. There I have the coefficients 7, 38, 13, negative 10 of f of x. And that means that the remainder here is actually 0. So the remainder is 0. And by the remainder theorem, that means that the f of negative 5, which in this case is c, is equal to 0. But I have this factor theorem up here that says if the f of c is equal to 0, which is the case I have here by the remainder theorem, then x minus c is a factor of f of x, which would mean that x minus negative 5 is a factor of f of x. And you can see here by the division algorithm it's actually true, because x minus negative 5 is x plus 5, and here would be the quotient, where here are the coefficients of the quotient, so that would be 7x squared plus 3x minus 2. And then the remainder is 0, so by the division algorithm we get this, and since we don't have to write plus 0, this is a factored form of the original polynomial f of x. So this is one factorization of it. So that means that negative 5 is one of the zeros of this polynomial based on this synthetic division. What if I wanted to find the other two zeros of this polynomial? Well, the other two zeros of the polynomial are the zeros of the quotient, because we already have negative 5 as one zero. So we would need to find the zeros of 7x squared plus 3x minus 2. We can use the quadratic formula since this is a second degree polynomial. And the quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Plugging in the values of a, b, and c, which are 7, 3, and negative 2 respectively, we get this. And then when we simplify, we get this, negative 3 plus or minus the square root of 65 over 14. These are the other two zeros of the polynomial. So this polynomial has three zeros, and I'll list them here. They are negative 5, which was the original one from the synthetic division, negative 3 minus the square root of 65 over 14, and negative 3 plus the square root of 65 over 14.